Right, okay. Yes, so I'm Piotr Dudek I'm at the University of Manchester, and the title of the talk is SCAMP-5 Vision Sensor with Pixel Parallel Processor Array. I'll take it easy after the lunch to remind ourselves why we're here, right? So we're here because vision is hard. So that's what we're doing. But there's another aspect to it. If you're designing embedded systems, even if you know the algorithms, if you figure out how to do things, you may still run out of CPU time or GPU time or power in your embedded system. So it's also hard because to do things on embedded systems in real time, you need billions of operations per second performance or trillions of operations per second at a power budget of milliwatts. So that's the challenge. And I mean, this morning we've already talked about this. Conventional vision pipelines might not be the ideal solution to embedded vision processing. In a conventional system, you start with this image sensor, you digitize the information, you send lots and lots of images to your compute system. So GPU, CPU, whatever you can throw at it. And what is really happening is that there's a lot of data shuttling around in a system like this. So there is. Is it working? So it's a lot of images coming from the sensor, which is lots and lots of pixels, and then those pixels get into the processors talk to the memory, the CPU talks to GPUs, and it's passing all this data around. And it's really the data movement that is critical for the power consumption and the performance of the system. In the computing systems, processing is pretty much free, is moving data around, which costs time and costs power. And so the solution that we've been exploring in this community is, well, getting rid of the conventional image sensor and replace it with something a lot smarter, something that will process the information on the sensor itself and send not the streams of images or image frames to the processing system, but some other meaningful data. And if you do this, you can get rid of all this stuff and replace it with something low cost, low power. And it's really very easy in PowerPoint. It just happens and it works. But it is a real thing. The processing, putting processing where the data is, really gives you high performance, high speed, low latency, higher capabilities, and a much reduced power cost and size of the system. So putting that processing at the front end does have these benefits. Now, we talked in the morning about event cameras. And really the principle here is that you want to create some sparse, high temporal resolution data that you extract from the images. Okay, and we've seen the examples of things that people are doing with DVS, Davis, Hattis, all these cameras that are available, and they are detecting log intensity changes and signaling this through an event. So something interesting has happened in the image. That's the sort of extraction of the information that you do on a sensor. But if you want to think about it in more general terms, it's only one type of feature that they extract, one type of temporal feature, this log intensity change. And to be controversial, I could say perhaps that's not the right one, that's not the most useful one. And a lot of people who are trying to build systems that take the data from those processors and understand how difficult it is. Because sometimes the algorithms that we understand, that we know how to build, don't yield itself very well to this new type of data. So it's both a challenge, an interesting challenge, but also perhaps we can explore further that space of things that we can extract before we transmit data of the sensor. And just as a side note, biology does a lot more on the retina than just extracting log intensities. So there's a lot of computation being performed in the retina. We talk often about biological inspiration for the systems. There's a lot more computation that goes on the retina. So how about other types of spatial and temporal features? Can we produce events that correspond to moving edges? Maybe we can produce the events that correspond to corners in the image. Maybe we can do some more general spatial temporal convolutions. And then how about a more abstract features, so some more complex information extraction? Can we detect centroids of the objects, or can we do entire visual odometry on the sensor itself? Okay. So my question really was how we can construct now a vision sensor, the compute substrate that can do all this. Okay. And so we have this variety of tasks and algorithms that we may want to do, and we want a device that is flexible and can do all these things on the sensor plane. Well, you tell me you need a computer to do that, right? If you want a system that is very flexible, we know how to do this. we have this idea that we can build computers, essentially a system that has some processing power, some memory, and a program that directs how these operations fetch data from the memory, do something, and put it back, and so on. So this general paradigm allows us to use a very limited hardware, but do infinite number of things with it. Okay. And there is another aspect which is particular to early vision processing, is that we're dealing with compute-intensive tasks. Okay. And they're compute-intensive not because they're very difficult, kind of either conceptually or kind of mathematically in terms of the processing that you need to do. They're relatively simple operations, and they're identical for every pixel, and they're localized, so you only need to talk to your neighbors. It's just there's a lot of it, and so that's mostly what the challenge is. But when we have a lot of identical things to do, the same things done on every pixel, we know how to do this. We can build a massively powered processor array, and that's why whether you use a DSP system which has a vectorized processing, or you're using a GPU, you're really using this idea that you have this many processing units that do things in parallel. They pretty much do the same things, but on different pieces of data. And if you want to go faster and lower power, well, you can just more processors, right? And the more of them, the better. And if you go into the extreme, you could say, well, I could have one processor per one pixel, right? If my task is pixel parallel, if I do the same things for every pixel, then I could put a processor in every pixel. And where rather than having my processor per pixel, we could put a processor inside a pixel, really inside the image sensor. So that's really the idea, which is similar to the event sensors, which put some processing circuitry into the pixels to extract log intensity changes. Here we will put like a more generic processor into a pixel. So that's really what a vision sensor with pixel parallel array is, okay, or pixel processor array. We have this camera that will take the light that will fall upon our image sensor, and what we're putting in there is a pixel processor array, an array of pixels, but each photodetector is associated with a processing circuitry. A full-blown processor. And so what we can do now is just send software instructions to the system, and what we can get out is, well, whatever we want, because we can write programs. We can extract whatever type of information in whatever form we want. And one of those would be creating some sort of events that correspond to higher level things happening in a system. The challenge, of course, is now how you design this, how you get to a point where you can put a complete microprocessor into a pixel. Okay, so that's not a trivial thing, and so designing this processing, and I will not tell you how it's being done, but that's the kind of work that we have been doing in Manchester. Okay? But once you are able to design a small processor, then you can then just write program A and get an output A. You want to change your task, you write some other program, while your sensor becomes a sensor doing something else. You write your third program, you compute some other operation. So it's a fully flexible system where you can decide what kind of events you're producing. And they don't have to be events, they could be also two-dimensional maps, they could be other data structures. So we just built a lot of those processors and built a chip, okay, a custom chip that does all this. So this is the device that we've built and we are demonstrating in the other room. It's called SCAMP-5. And it has 65,000 processor cores, if you like to think about it. 65,000 simple processors that work in parallel. So those processors are relatively primitive. They have very small amount of local memory. They run at a very slow clock. It's 10 megahertz clock. Okay, so for people who design microprocessors, that's a very slow system. But there are 65,000 of them, so we can still get about 600 billion operations per second out of the system at about 1 watt of power. Okay, so that gives you an efficiency of about 500 gigaops per watt, which is a decent number for state-of-the-art processing system these days. Okay? But one thing that has to be also remembered is this is fully generic. You can write your software and customize fully to your application. And this chip is a university project. It's an academic exercise. It's been designed in 20 years old CMOS technology. Okay, so that technology was state-of-the-art 20 years ago. It's 180 nanometer CMOS. Okay, just briefly, what is inside each processor? Okay, so it's a processor that it's a slightly weird in a way. data path operates is a mixed analog-digital data path. Some of the operations are carried out directly on analog numbers without converting it to digital. I won't go into detail into this, but we have about 6 registers that can store analog information. You can have additionally 13 bits of digital information. And you have a very simple instruction set that can move the data around. It can add numbers, subtract, divide by 2. They can do some conditional instructions. And then you have the entire support circuitry for the control and the interface and random access I/O and so on. One of the things, so you can scan the array and get the images out. You can also summarize some information, so calculate an OR operation on a part of the array or the entire array, or a summation of the values in the entire array in an equivalent of a single clock cycle. And you can also do pixel-driven I/O, which is when your outputs of your algorithm is a sparse set of points. You can read them out as events, as addresses of those pixels, rather than sending out the entire array. So if you have an algorithm that requires some sort of event type of address, event output, once you've sparsified the information to that binary array with only a few points, you can read out those events. And we have built an entire system around it, which consists of this vision chip, which you can think about it as some sort of accelerator for the microprocessor that is running and controlling that system. And that is a conventional ARM microcontroller. So you almost like to write a code for the ARM microcontroller, but whenever you have something that needs to operate inside the sensor, you have like an inline code. I have an example actually. You have an inline code that runs on the sensor itself. Okay, so this is, and you just use regular compiler to compile your code. So you write a code in C, and you put this kernels that will be executing on the accelerator, on the processor array. And those kernels are written in assembly language. We don't have, at the moment, a working compiler. But because the processors are very simple, it's very easy to code in assembler. Okay. And we've also built an entire software development kit that allows you not only to write the code and compile and run it on a system, but also like an instruction set simulator or emulator that allows you to debug the programs, step through the code, see what's inside all those registers inside the chip, and develop your software in that way. And there's a lot of effort that actually goes, and it's very hard. I cannot emphasize how difficult it is to do these things in academia, where your currency is papers, and you can spend 2 or 3 hours, writing the stuff around the sensor, and you cannot write a single paper about it. But you have to do this if you want to use it for something. So we can test it on a lab bench, or we can try to give it to people and do something with it. And our ambition always was to demonstrate this in applications. Okay, so just to recap, so that we kind of summarize this processor, and then I'll show you some examples. So we have this pixel processor array where each image pixel contains a processor. Okay? These are completely software programmable processors. They execute code. And all computations are carried on the sensor itself in a pixel parallel array. So we're minimizing the movements. We never sending data from the sensor somewhere else. We don't do a lot of transfers between the processor and memory, because memory is also dead. So everything is local. And that gives you high speed, low power, without quantifying at this point. But and so all the examples that I will be showing are done on the sensor, and then only the outputs are visualized. I sent to a computer for visualization. The operation here is really frame-based, so it's a bit of a heresy for the event community. But we're really running this with frames because we have algorithms. We capture the image and we run that algorithm and then run it over and over and over again. But we can run them very high, so we can run at the frame rates of kilohertz or faster if we want. So in a way, we still offer high temporal resolution because we can run very fast those frames, because we never take the frames out of the chip. Only interesting data is transmitted out, so this will be the results of computations. That could be 2D maps, there could be some segmentation map, there could be some global measures like a vector of global motion or something like that. Or there could be address events of points of interest, if that's what you're trying to do, trying to extract some points. Maybe these are contrast change events, but maybe it's something else. I'll show you just a few examples of what what we've been doing with this, this is some basic algorithms that, this is like image processing 101, and you can do your edge detector, you can code the, so this is running, I'm outputting here both the input image and the output image from the sensor. There's a short code that is, I don't know, maybe 50 instructions or so that implements a sub-L filters, horizontal, vertical, and absolute value of the, and the summation of the two. So it takes about 5.8 microseconds. It consumes about 5.2 nanowatt per pixel if you want to look at it that way. This is a the second example I have is a median filter. This one runs and sorts pixels in the 3x3 block and picks out the middle value. So something a little bit more complicated. And again, this is pretty easy to run. I sometimes get questions. I haven't gotten too much into the processor architecture, but because those computations are on a not only limited precision values, but values that are somewhat noisy sometimes. Sometimes people ask how does the fact that the processors are mixed signal analog processors, how does it impact computations? So that just shows you, there is a little bit of, if you compare ideal numerical median filter with what you can achieve on the sensor, it's a little noisier. Okay, you can perhaps see a little, so you still can achieve your task, you get rid of those big spots that you wanted to do, but you perhaps have a little bit more noise. We have quantified that, and when you run a simulator, you have a model that allows you to model all these noise effects. Here I'm showing an optical fall. So we're using a simple block matching algorithm, which is take a 5x5 block and see where it matches better from a frame to a frame. And again, we can run it at, so this is just someone waving at the color codes for the direction. And you can run it again at thousands of frames per second, that algorithm. Here is a corner detector at the bottom. So here, the kind of rainbow is just a history of events. So here we're sending the events, but the events are computing as corners. And we use a fast corner algorithm. Basically, you take the middle pixel, you look in a circle around, compare your magnitude of the pixel from the ones around, and count how many of them are either bigger or smaller than you. So it's a relatively simple algorithm, but here you can see, and then we just send one event when there is a corner. Yeah, so we just extract the corners, and everything that comes out of the chip are corners. So we can run it at about 500 FPS in this example, because we are still sending gray level frames so that you can see actually what's happening. If I run things without sending the gray level images out, only sending the events that correspond to the corners, then we can run about 2000 frames per second. So with half a millisecond resolution, we can get a corner map. So these are highly informative events that are still at a high temporal resolution, but they do a lot more and potentially are more useful further on down the chain than a simpler type of event. To push it as far as we could, we implemented this 100,000 frames per second intelligent task. And we get a drill, a high-speed Dremel drill. And onto this, we put objects which are closed and open objects, O's and C's. And the purpose of the algorithm is to demonstrate how fast you can go, but the task is to capture an O among the C's. Okay? So find an O and find the center of that O, and that will be only one event that we will be sending out. Okay? So, and do it as fast as possible. So we're able to complete the algorithm in 10 microseconds, which gives you 100,000 frames per second processing. Okay, and that actually, so this is an, yeah. So you just pick one point and that's your event. So this is now, as this really is spinning, you can see that we only send just one event per frame at 10 microsecond time scale. We return one frame just so that you can confirm that we're going through that all, that we do the task. So that's somewhat contrived, but showing how fast you can go with the frame-based if you don't actually have to send the frames out of the sensor. This is a more kind of practical example where we were looking at a microfluidics application where we were trying to track particles. And this is done through a microscope. So they're not maybe that clean, and you have to maybe do background subtraction, clean things up, segment, find the center. So it's a relatively simple image processing algorithm. But we can run the whole chain at 2000 frames per second. Again, never outputting any frames, just outputting the coordinates of the particles that we find. And this is now a plot that shows, that's basically a time, and this is a location of the particle. So you can see how we're able to find where this kind of routes that the particles take. So that was done by Javier Bertholon at the Sorbonne University. There is a bunch of things that was done in collaboration with ETH and the University of Zurich by Julien Martel, and that's on what I would call subframe computation. Is where we do a lot of computation within a frame, but what we're interested in is maybe an output that summarizes that computation as a single frame at a lower speed. One of the things is high dynamic range sensing, where we take lots of different exposures, short and longer, so many different exposure times, and then build up a high dynamic range picture out of that. So we were able to, essentially with no latency, because once you've integrated for the longest time, you have information of all your integration times, and you combine them in some intelligent way so that you equalize the brightness across the image. So you can see either all the things are visible here. I think this is my timer. Okay, I still have 2 minutes. Here's depth from focus, which is another thing where we have a lens that is oscillating, like going focus in and out of focus very quickly at 60 hertz, and we can capture 128 frames during that one sweep and find out which is the sharpest, and the location where it's sharp gives you the distance, because that gives you the setting for your zoom, right? So you capture all these different frames, and different things come into focus at different times. You find out at what time they are sharpest, and you can create a depth map that tells you how. So it's a monocular depth just by oscillating very quickly a liquid lens. And that runs at 7,000 frames per second for processing, because we need to analyze all those frames. So that's a kind of method that no one would do on a conventional sensor, because you would need to send so many frames out. But because we can process all this internally, we can afford those very high frame rate processing. There is a bunch of things that we're doing with the University of Bristol. I don't have time to show any videos, but we've been doing visual odometry, where basically the camera locates itself based on what it sees, applying that to flying UAVs, doing tracking of some robots, doing a high-speed control where a car goes through the gates and so on. If you're interested, we have all videos on the project webpage. This is a CNN demo that is running outside. If you want to have a look, we implemented a layer of convolutional filters and a pooling layer, and again everything is done on the sensor. The demo is outside. If you go there in a coffee break, we can tell you more about it. That's been done by the guys at Bristol as well. Okay, so just to quickly now, where this is all going. I've been working on the sensors for a very long time, and we've been developing this SCAMP line of sensors that I talked to you about. We've been building some other pure digital and different kind of multiprocessor systems. We've just taped out a new SCAMP, is SCAMP-6, which was a small one, and SCAMP-7. So that's the current project. But I think it's important to realize that all this is a technology that is 20 years old, okay? So that was the state of the art in 1998. If we use today's technologies in terms of the number of processors, in terms of performance, we can really do lots and lots better. So this is now state of the art performance. We can go multiple orders of magnitude over state of the art if we really use the latest technologies. We have a few cameras, we've built a few, and we are capable of building a few more. So if people are interested, we would like to put them wherever we can. So get in touch with us if you think you may want to use a system like this. We are happy to. You can certainly use a simulator, and if it looks promising, we can lend you hardware and we can collaborate. And that's it. There is a bunch of people that worked on it, both in my lab and in collaborating labs, and we're grateful to our funders. Thank you very much.